All right, now let's come to the MPI or distributed memory implementation. How would you implement this in distributed memory? Well, for reduction, we will just substitute, instead of using hash pragma-omp with reduction variables, we will basically be using MPI reduce, or I can even use MPI all reduce, right? Okay, so I can use either of these calls. It does the same thing, right? You can specify min operation and it will reduce it on one node, and then you can broadcast it to all the other nodes. Or the equivalent of reducing it to one node and broadcasting to all the other nodes is MPI all reduce, which does all of this and gives the final reduced value on all the nodes. Again, you can use your own primitive data type, or you can call reduce twice to get the vertex ID. Okay. So this part is clear, right? The first one is clear. So now let's come to the second one. Okay, so even before we talk about reduction for the first step, now I need to be careful. What are the vertices assigned to a processor? So again, I'll go with 1D distribution. Right. So each processor has, or rather owns, n by p vertices. Right. What are these n by p vertices? I can do it block by block. The first n by p vertices go to node 0 and so on. And what I'm doing is I'm distributing my W matrix. Right. This is distributed amongst the processors. So I'm going to assume that my W matrix is so large that it cannot be held on one processor. Otherwise, I mean, I can just create a copy on all the processors, right? But that's not what I want to do. So distributed amongst the processors. Okay. Right. But how do I distribute it amongst the processors? Do I distribute it row wise, column wise? How do I do it? So typically what happens is that in most algorithms, right, you typically distribute it row wise. So you distribute the row amongst the processors, which means that each processor knows all the outgoing edges to other vertices, right? It keeps track of all the outgoing edges from that vertex. So Prim's algorithm is quite simple, but one interesting aspect of Prim's algorithm is how do you do the data distribution in a 1D manner? So let's look at this operation. Now let's come to this part, right? We've already taken care of the first part. We said we'll use the MPI reduce operation instead of the OpenMP reduce operations, right? So that part is okay. Now what do I do over here? So again, this U can be broadcast to all the processors. So all of that can be taken care of. How do I take care of this last for loop? So again, I own my vertices. What do I have to do for each of these vertices? If I'm the owner of V, I will have my D of V value also. So how is the D matrix distributed? So that's also distributed amongst the processors. This means their D values and their W portions, right? These are maintained by each processor for their own vertices. Okay. So each processor has the D value for the vertex that it owns. What else does it need? It needs to compute the min over this value that it already has and WUV and update DV with that. Now, where is WUV?
Owner of U.
Owner of U. Yes. So this is where the important data distribution aspect comes in. What I'm going to do is I'm going to divide this matrix not row wise, but column wise. Okay. This is an incoming edge into V, right? I am the owner of V and UV is an incoming edge. So I want to keep track of, or I want to have the information of all the incoming edges, not all the outgoing edges. So if I want to keep track of all the incoming edges, I just distribute the W matrix column wise. Is that clear? So if I distribute it column wise, then what are all these edges in a column of for V? All the entries in the column of V are basically edges of the type U, V. It would have the weights for all the incoming edges into V. And that's precisely what I want. Okay, so there are these small subtleties when you go to parallel programming and distributed parallel programming. Data distribution is a very, very important aspect. Okay. OpenMP is generally quite simple. There are not many challenges when you programming in OpenMP, right? They're just a few hash pragmas that you have to insert here and there, and typically you're done, right? Of course, there are other algorithms for which you have very complicated OpenMP implementations, but I'm just saying in general. But MPI, typically you have to do much more work. And one of the things you have to do is the data distribution is a very important aspect, right? And we've seen for BFS also in terms of data distribution, right? The 1D distribution row wise of the adjacency matrix. And here what we are saying is that, the column distribution works better for Prim's MST algorithm. Okay. So that's the MPI implementation. Now, let me just wrap this up with a few comments. So what is the time it takes? Sequential time is n square, right? What is the parallel time? Well, what about the computation? The computations were just distributed amongst the P processors, right? Nothing else was really done. So n square by P is the time taken for computations. What about communication? So communication, again, if you're talking about P processors and you're doing operations of the type reduce and broadcast, these will take log P, as we discussed, right? Just like in a tree, binary tree. It will take log P steps to do the reduce. You're only sharing constant size information, so there'll be some constant involved. Let's not worry about that. And then you have to do this for n-1 iterations, right? So it's going to be theta n log P. That's the total communication. Okay. So one of the things that we are interested in is speed up. How do you calculate speed up? Speed up is basically the sequential time divided by the parallel time. In an idealistic scenario, we want the parallel time to be 1 by P times the sequential time, which means it would give a speed up of factor P. So if I'm putting P processors, I expect a speed up of factor P, but that doesn't always happen for all algorithms, right? So in this case, what's the speed up? The speed up is, so this will be theta n square, and this will be theta n square by P plus theta n log P. If you divide by n square everywhere, so this is 1 by theta 1 by P plus theta log P by n. Okay. And then there is a concept of efficiency. What is efficiency? Efficiency is basically speed up by P. I mean, if I'm putting P processors, I expect a speed up of factor P, right? And efficiency just scales it to a level of 0, 1, right? So it just divides by P. So ideally, I want an efficiency of 1, which would mean speed up of P, right? It's the same thing. So these are just standard terms used in parallel computing literature, right? So what do I get? Well, I will get something like 1 by 1 plus theta P log P by n. Okay. What's the implication of this? What I am interested in is efficiency of 1 or constant, right? Asymptotically constant 1. But how many processors should I put in? If I put in n processors, my problem size is n. If I put in n processors, I am not going to get an efficiency of 1 asymptotically, right? Can you see that? So it's going to be of the form 1 by 1 plus n log n by n, right? Which is what? 1 by 1 plus log n. So I did not achieve what I wanted, right? So I want a efficiency of 1. So how do I do that? Well, if you just take n by log n processors instead of n processors, right? So if you have a problem of size n, don't put n processors, put n by log n processors. As long as you put n by log n processors, you will get an efficiency of 1, right? So this will become 1 by 1 plus, what is this expression going to be? P will be substituted by n by log n. What is log of n by log n? That's pretty much log n, right? And then you had this division by n. Okay, so this log n cancel out, and then this n cancel out. Okay, so you get a constant. Asymptotically, this is the best you can do. So there is always the theoretical side and the practical side, right? Theoretically speaking, this is what you do, right? You put in n by log n processors and you'll get perfect speed up to that level. practically speaking, you can never put in so much processes, right? You're typically dealing with huge problems and you have much fewer processes to deal with. You can't compare the number of processes with the graph size that you're dealing with. Okay, the number of processes is much smaller, right? So practically this doesn't carry much value, but it's still interesting to know from a theoretical perspective.
So you're saying that putting n by log n processors was better than n processors?
Yes. That's what this efficiency number is showing you, right? With n processes, you only get an efficiency of this. This is smaller than 1, right? Asymptotically, it's smaller than 1. This is smaller than a constant. We've achieved a constant by taking p to be n by log n. Okay.
The efficiency is not still 1, right? It's 1 by 1 plus 1, not 1 plus 0.
Yeah. So constant, right? Constant. That's why we are aiming for constant, not for 1.
Okay.
Asymptotically 1, that means a constant, right? So you can never get efficiency of 1, but asymptotically you want to do the best possible, right? So this is a constant, which may be 1 by 4 or whatever, right? But what is this? This is 1 by log n. Asymptotically, that's pretty bad, right? Compared to half or 1 by 4. So again, we are only looking in the asymptotic sense.